The United States Air Force are right now still flying an aircraft that just looks like it shouldn't exist anymore. This jet was designed with slide rulers and built for a world that supposedly disappeared decades ago. It's also decades older than the pilots flying it, and it's actually old enough that the fathers or even the grandfathers of many of them also could have flown it. And as it looks right now, it could still stick around long enough for another generation or two to fly them as well. I am of course talking about the fantastic B-52. In the airline world, tri-jets and quad-jets are now almost gone, and yet here it still is, with its 8 engines. No airliner has ever used that arrangement, and no engineer drawing up a clean sheet design today would ever even consider putting 8 engines on it. On top of that, continuing to use engines that were first introduced when televisions were still black and white would be utter insanity. So why did the B-52 keep these engines for so long, and why did the Air Force finally decide that now would be the right time to replace them? Well, that's not even the biggest mystery here, because you would think that since the US Air Force is finally swapping out those 8 old engines, they would take the chance to maybe replace them with 4 new engines instead, right? Well, no, they're not. Instead, the coming updated B-52s will still have 8 engines. So why are they not taking the opportunity to simplify this strange engine layout? Well, as it turns out, that decision wasn't obvious, nor simple or quick. Behind the scenes of this effort to buy engines for a shrinking fleet of ancient planes is a story about the limits of Cold War engineering, the challenges of updating a 1950s airframe for the 2050s, and it involves a re-engineering effort so complex that it will take more than 15 years to complete. Now, before we get into this story, it's worth remembering what the B-52 actually is. This is an aircraft that first flew in the early 1950s, at the height of the Cold War, when the United States needed a bomber that could sit on nuclear alert and, if necessary, fly halfway around the world to deliver those weapons. Its design roots go all the way back to a time when long-range flights meant navigating with papers and pen, and when a jet-powered bomber was quite a radical new concept. And yet, despite dating back to that bygone era, the B-52 has now flown in nearly every major US conflict since its inception. It has been used over Southeast Asia and the Middle East, dropping simple, unguided bombs, and somehow it still remains useful today thanks to updates that allows it to carry guided missiles that can now be launched from hundreds of miles away. Now, you might be wondering why the Air Force hasn't retired this plane long ago, and the answer is that it's not from a lack of trying. Several newer planes were supposed to replace it, like the B-58 and the B-70, and more recently modern jets like the B-1 and B-2, but somehow the B-52 has stubbornly managed to outlive all of them. Of course, the B-1 and B-2 are still around, but they will both likely be retired decades before the B-52. Now, I'm not going to go into why the plane itself stuck around that long, but if you think it's simply because the Cold War ended, well, then I'm not sure that you've recently seen how things are, but things are getting a little bit colder again. And while there are plans for newer jets, the US Air Force so far isn't changing its mind about keeping their beloved B-52s. So let's therefore go back to the engine upgrade, making this new lease of life possible, as well as the engines that sit on the B-52's distinctive twin pods today. You see, even though these are not the very first engines to power the B-52, they still date back to a time even before humans had flown in space. The B-52s flying right now are all B-52 Hotel models, delivered in the early 1960s, and each of them is powered by 8 Pratt & Whitney TF-33 turbofans, a design that traces its roots back to the very dawn of the jet age. They are low bypass turbofans that first ran in testing back in 1958. And there was also a commercial version of the TF-33 called the JT3 Delta, which powered some versions of the Boeing 707 as well as the Douglas DC-8. Back in its day, this was a modern engine. Earlier versions of the B-52 used the even older Pratt & Whitney J57 or JT3C in commercial use, who actually also powered earlier versions of the 707 and the DC-8, by the way. Now, for decades, using these TF-33s wasn't a deal breaker. These engines weren't exactly spectacular, but they were reasonably reliable, and perhaps even more importantly, they were very common. The fact that they were used on both civilian 707s and military transport planes like the Lockheed C-141 meant that maintenance shops were very familiar with them, and spare parts were therefore easy to find. But obviously, that world is now long gone. The airliners that once shared these engines were retired decades ago. The overhaul shops closed, and the suppliers who built many of the core components don't even exist anymore. As a result, the Air Force has recently been sustaining these B-52's engines by cannibalizing old stock, reworking parts and dipping into an ever-shrinking reserve of spares. Actually, for decades now, the Air Force have been on the lookout for old civilian 707s with JT3 Delta engines that were being retired so that they could stock up on engines and spare parts. Some KC-135 tankers were also upgraded with engines from 707s in the 1980s before getting upgraded again later with CFM56s, and I guess then presumably their 707 engines were used to sustain the aging B-52 fleet as well. But obviously, this couldn't go on forever. According to the Air Force's own experts, the TF-33 will become completely unsustainable around the year 2030. Just because the industrial base needed to keep it alive simply won't exist anymore. And without the necessary parts, there will be no safe way to prolong these engines' lives any longer. Now, even if parts weren't an issue, the fact that the TF-33s come from another era means that they also require much more maintenance per flight hour than anything comparable to them. And they also produce less electrical power and obviously burn far more fuel than modern jet engines do. Actually, to demonstrate just how out of date this engine is, you only have to look at its bypass ratio of 1.5 to 1. You can compare that to the nearly 11 to 1 ratio of the LEAP 1 engine series that we use on the 737 MAX and Airbus A320neo families. Now, you might think that the military doesn't care about engine efficiency as much as airliners do, and up to a point that would be correct, at least as far as the economic side of things are concerned. But the Air Force do definitely care about one thing, and that's the range of its aircraft. You see, even when they use multiple air refuelings, in order to fly halfway around the world, the crews still have to ensure that they can always divert if they wouldn't be able to pick up more fuel in the air for some reason. So, newer engines with better efficiency means much greater range with onboard fuel and therefore much easier flight planning. But if these old engines have to go, then what do you replace them with? And why on earth would the Air Force still insist on keeping 8 of them per aircraft? Well, I will get back to that, but before we do, I want to point out something else here. You see, while researching this video, my team and I went through loads of public material and videos, some of it coming from official databases, which are controlled by official authorities. But that's not the case with your personal data. Instead, your info is likely right now being spread over hundreds of different websites with very little regulation protecting it. And that makes it surprisingly easy for data brokers to harvest things like your address, phone numbers, and social security details, and then sell it on completely legally. But that's where today's sponsor, Incogni, comes in. They will continuously scan the internet for all traces of your information and then force those data brokers to completely remove it. And their new custom removals feature puts even more power in your hands, because now, if you find your info somewhere like in a spam email or something, you can submit those details directly for manual removal through your Incogni dashboard, instead of waiting for their teams to find it. And Incogni will then work on them, 3 at a time, in the order that you upload them, which is awesome. So, to get started and get a whopping 60% off the annual plan, scan this QR code or go to incogni.com/mentor now, and remember to use the code MENTOR NOW at checkout. Thank you, Incogni. Now let's continue. So, why isn't the US Air Force replacing those 8 TF-33 engines with 4 modern high-bypass turbofans instead? Each of those TF-33s produces around 17,000 pounds of thrust, so a pair of them could be replaced by one single Pratt & Whitney PW2000 engine for the Boeing 757, for example, since it generates between 37,000 and 43,000 pounds of thrust. Now, I'm using that engine as an example because the Air Force is already using it under the designation F-117 to power its fleet of Boeing C-17 transport aircraft, as well as its military 757-200 variant, the C-32 Alpha. And also, weight-wise, one of those engines would be lighter than the 2 TF-33s. Now, the PW2000 also isn't a new engine anymore. It dates back to the 1980s, but it is a high-bypass turbofan who is also a known quantity to the Air Force, like those old TF-33s are. So why not use engines like these, simplify some aircraft systems, and give the B-52 the kind of layout that we all consider normal today? Well, the answer is that going from 8 engines to 4 would be much more than just a straightforward engine replacement program. Even if they wouldn't be heavier, the more powerful engines would very likely need a partial wing redesign and perhaps even modifications to the plane's wing box. And why? Well, the B-52's wings was designed in the early 1950s around the thrust, weight, aerodynamic interference and vibration characteristics of 8 small engines spread across its span. And those engines act not only as power plants but also as aerodynamic devices. Each engine pod and pylon acts like a wing fence, controlling span-wise airflow across the wing and helping the aircraft behave predictably throughout a big range of speeds and altitudes. So if those narrow pods would be replaced with the larger nacelles of 4 high-bypass turbofans, a lot would likely change. The bending moments, torsion and flutter characteristics of the wing could all be different, and a lot more aerodynamic testing would therefore be needed to see if structural reinforcements would be necessary to keep things safe. Also, losing 1 out of 4 engines, it's very different from losing 1 out of 8. The asymmetric thrust loads after an engine failure would be much higher with 4 engines than with 8, which then subsequently would mean that the rudder and tail surfaces would need to be bigger. And once you change the tail, you've also changed the stability characteristics of the whole airframe, which of course is a huge deal in itself. Then there is the ground clearance. The B-52 is a high wing design with a lot of anhedral, meaning that the wings are angled downwards, putting the tips of the wings closer to the ground. And that means that its outer engine pods are already sitting quite low. The larger diameter of modern high-bypass turbofans could therefore require a taller landing gear, or even more radically redesigned pylons and structural work to the wing. And then there's the plumbing for fuel and for other systems. You see, with its 8 engines, the B-52 is designed to drive various onboard systems with electrical, pneumatic or hydraulic power in specific ways under different scenarios. So going from 8 to 4 engines would require a complete redesign of all of those systems, as well as rewriting the manuals for the crews that will operate them, of course. So all in all, going over to 4 engines would create a plane with new stability characteristics, new aerodynamics, extensive structural work on its wing and possibly its landing gear, as well as completely redesigned electrical, pneumatic and hydraulic systems. Basically, making a 4-engine B-52 would be like certifying a completely new aircraft, which would be expensive. Really expensive. This is something that the Air Force already knows, because they have studied this before. First, they looked at this in the 1970s, then again in the 1990s with Rolls-Royce RB211 engines, the other 757 engine option by the way. Every time the conclusion was the same. The modification would cost billions more than it saved, take longer, introduce substantial risk, and deliver no operational benefit large enough to justify the transformation. Now, some of the Air Force's financial calculations used to draw those conclusions were later disputed, but more recently, with aircraft certification costs going higher and timelines getting longer, the Air Force seems to have finally made up its mind. When the re-engine program finally became unavoidable, they have now asked for 8 modern new engines, as close as possible in weight and thrust to the originals to avoid touching the airframe at all. But what engines would that be then? Well, the requirements for this were so narrow that only a few modern engines even came close. General Electric, Pratt & Whitney and Rolls-Royce all submitted proposals based on proven commercial engines used by business jets. And the winner, announced in September of 2021, was Britain's Rolls-Royce, to the surprise of many. Specifically, the Air Force chose the F-130, which is the military name for the Rolls-Royce BR700 that powers the Gulfstream G550 and the G650. The Air Force are familiar with this engine because they fly it in military Gulfstreams called the C-37 VIP, plus some communications aircraft. And that familiarity was a big plus. And Rolls-Royce even offered to build the engines domestically in the US, in Indianapolis, Indiana, making it a little bit more American. Now, the F-130's size, thrust output and mass flow characteristics are close enough to the TF-33s that the Air Force can install it with relatively modest changes to the nacelles and pylons. And yet, in performance terms, it is a true generational leap. With a bypass ratio 3 times higher than that of the TF-33s, the F-130 is dramatically more efficient. It will consume 30 to 40% less fuel. Plus, it's more reliable and it produces plenty of extra electrical power, which the upgraded B-52s really needs for a new radar and future avionics. So this means that the Air Force will now buy 608 of these new Rolls-Royce F-130s plus spares under a multi-billion-dollar contract. And it will then begin a transformation of the B-52 that's so significant that when it's over, the aircraft will receive a new designation for the first time since the 1960s. The B-52 Hotel, the last of the Cold War bombers, will officially become the B-52 Juliet. But it later turned out that the real work only really began after the engines had been chosen. Because fitting a 21st century engine onto a 1950s airframe turned out to be far more complicated than anyone wanted or believed. On paper, the re-engineering effort looked relatively simple. Take off the old engines, bolt on the new ones, update a few displays and then call it a day. Sort of. But in reality, it turned out to be one of the most complex modernization programs that the Air Force has ever attempted, or at least during the last few decades. You see, almost nothing on these B-52s was designed with future engines in mind. So even though this was still 8 engines, everything from the pylons to the nacelles and even the airflow around the wing had to be revisited. And one of the biggest surprises came almost immediately. You see, the engine inlets just didn't work. When the engineers began modeling the airflow around these new nacelles, they discovered that the geometry of the old pods combined with the characteristics of these new engines created distorted and uneven airflows at certain angles. And despite having similar air mass flow characteristics to the old engines, these modern turbofans are much more sensitive to inlet disturbances than the old low bypass designs were. This meant that some of those new airflow patterns could cause performance loss, loss of stall margins, and even severe vibration issues. All of this led then to the inlets being redesigned and tested, first on computer models, then in wind tunnels, all of which added close to a year of delay to the project, pushing back key milestones. And that was just the airflow issues. Next came the systems. Like I said earlier, the F-130 produces more electrical power and also uses digital engine controls, but the B-52 it's being installed on has to date been fiercely analog. So Boeing had to run new wiring and integrate a whole new electrical architecture, both to control the engines and for that extra electrical power that I mentioned before, on top of replacing the analog cockpit instrumentation with digital displays. So this meant designing new interfaces, new data buses, and of course validating everything under safety and redundancy standards that were written decades after these planes first took to the sky. Then everything needed to be tested and validated. After all, this is a nuclear-capable bomber, which means that there is no fast tracking of anything. Meanwhile, the active B-52 fleet is still flying. The Air Force can't just pull all of its 76 aircraft into modernization at once, so they are now instead rotating through them, a few aircraft at a time, and that fact alone has further stretched the program timeline by years. And it doesn't help that the re-engineering program also overlaps with other upgrades, like the B-52's entirely new radar system. So all of the testing must be carefully sequenced to make sure that some changes made in one program doesn't invalidate testing in another. What all of this together means is that the first B-52 Juliets won't be operational until around the year 2033, and the rest of the fleet then won't get their new engines and upgrades until the mid-2030s. Now, there has been questions out there about how this could possibly take as long as it is, but as you can see, no one is dragging their feet here. It's simply because integrating 21st century technology into a 1950s airframe requires patience, precision, and the level of engineering caution appropriate for an aircraft meant to drop nukes. When the B-52 finally emerges as the B-52 Juliet, ready for another generation of service, it will be a 1950s bomber, ready to keep flying until the 2050s. The newest of these active jets came out of the factory in 1962, so that will mean that some of them could stay flying for over 100 years. And that actually says a lot about how the aerospace world works and how it's changing. The 1950s and 60s was an era when aviation was evolving so fast that military and commercial planes became obsolete within a few years. And yet, here is the B-52, somehow staying relevant for a century. This jet is an extreme example of something that we also see in a few other places in the aviation industry, that airframes usually outlast the technology inside of them. And sometimes modernizing an aircraft is all about replacing the parts that's holding it back. But on the other hand, the B-52 Juliet program also shows us something else. Design decisions can echo across generations. Whilst 8 engines made sense in the 1950s, they make absolutely no sense in 2025, and yet we still have them. Because the cost of undoing this 70-year-old design choice is so high that the world's biggest air force would rather buy 600 new business jet engines than change the airframe. And I think that this is something that companies like Boeing and Airbus need to keep in mind, especially when they contemplate the new designs that will replace the Boeing 737 and the Airbus A320 families. Because those aircrafts, whatever they will look like, should be as upgradable as humanly possible in order to remain competitive even if they stick around for 30 or 40 more years. Thank you so much for watching this video to the end. That really helps me. And I hope that you like this. Let me know in the comments if there's something about it that we've actually missed. Now, my patrons have been able to see this video before everyone else and have also come with great suggestions that have made this video better. And if you want to take part in the team and do the same, then scan this QR code or go to patreon.com/join/mentorpilot and sign up. My team and I would love to see you there. My name is Peter Hörnfeldt and you're watching Mentor now. Have an absolutely fantastic day and I'll see you next time. Bye bye.